Right, so moving along to think about where do all of these dissolved salts actually come from, we need to look at the addition and the removal of salts from the ocean. So this is going back to our thinking about concentrations in a reservoir that we looked at last week in the cycles module. So we have fluxes into, and we have fluxes out of the ocean. So we have fluxes in of salts and fluxes out of salts and of particular salts. And these, the balance of these salts results in the concentration that we actually see in the ocean. So let's have a closer look at those. This diagram here shows pretty much an overview of some of the behaviours that behaviours of salts that either add salts to the ocean, either via rivers, volcanic eruptions, weathering in the seafloor due to these hydrothermal systems. So they're all processes that add salts to the ocean, or dissolved ions to the ocean. And then we have the removal processes. The removal processes are sea spray, which removes salt, obviously, from the ocean onto the land. And then we have biological processes and sedimentary processes that remove the salts that precipitate onto particles, fall down and collect on the bottom of the ocean as sediments, and then ultimately are probably removed via subduction of those sediments out of the ocean realm. So to give you a little idea of those, so rivers are an obvious source of dissolved salts from weathering of rocks on land. These just show some images, this one on the left from space of the river, the Yangtze flood plume going past Shanghai here into the China Sea. You can see all of this sediment going into the sea. On the right here, this is in North Queensland, so this is a river shedding sediment onto the Great Barrier Reef Lagoon. These floodwaters or waters in the rivers carry a lot of dissolved salts of a whole range of descriptions. Sometimes they're dissolved, sometimes they're actually adsorbed onto the particles of the sediment, the clays, and when those clays get into contact with seawater, the salts dissolve from the particles and remain dissolved in the seawater. So rivers are a big one, a big source of salts to the ocean. We have seafloor hydrothermal activity along mid-ocean ridges. So beneath the 80,000 kilometre long mid-ocean ridge system, we have magma chambers, which are at very high temperature. Those magma chambers, which are the source of the mid-ocean ridge basalts and pillow basalts that get erupted along the mid-ocean ridges. These high temperatures drive circulation of water through the crust, through the oceanic crust. So they draw cold water down into the crust, and then that water comes up, it heats up, reacts with the rocks, dissolves minerals, and those dissolved minerals come out when the very high temperature fluids exit the seafloor into the ocean in the vicinity of the mid-ocean ridges. And if you go to these places in a submarine and you look around, you often find these black smoke events. So these are vents where very high temperature water of the order of several hundred degrees is exiting from the crust below at very high speeds and carrying lots of dissolved salts in them. And the water carries so much dissolved material and particulates that are precipitating from the water that the water in fact is almost completely opaque because there's so much material dissolved in there. Volcanic eruptions and aerosols are another significant source, particularly over the history of geological time. So volcanoes release gases which have dissolved components in them, and a lot of these gases go into the atmosphere and then precipitate those components into the ocean. And here we have a very big eruption of a volcano. I think this is possibly in Kamchatka from memory, and we have the volcanic plume going very high up into the atmosphere and then being transported out across the ocean, and this solid volcanic ash and dust is deposited into the ocean where salts and other elements are released and dissolved into seawater. Dust is another significant source of dissolved elements to the ocean. There's a big dust plume off the northwest coast of Africa, which you may be able to make out here, and Spain. So these dust storms can be very large. Another example here of a big dust storm in Australia back in about 10 years ago, back in September 2009, and you can see the big dust plume here with the northwesterly airstream carrying the dust across the coast into the Tasman Sea. This particular dust storm was estimated to have dumped 5 million tonnes of dust into the Tasman Sea. So if we now look at the sinks, so these are the processes that remove dissolved components, dissolved salts from the ocean. So one of the major ones is when we have, if I can get my mouse to move, so we have sinking clay particles or other particles in the ocean, or they could be organic material. As they sink down through the ocean, ions in the seawater often adsorb onto these particles, and the particles then transport the adsorbed ions to the seafloor where they accumulate. Here's an example of manganese nodules that form on the seafloor, and these are precipitates of manganese oxide that form more or less in situ on the seafloor, where manganese, like this, manganese is being adsorbed onto these nodules, and they grow with time. And in fact, in some areas, these can grow quite large, of the order of fist-sized sort of nodules that are just being precipitated straight out of seawater. So biology is particularly important because a whole range of plankton, whether it be phytoplankton or zooplankton, form tiny little shells or skeletons where the material that forms those shells and skeletons is actually extracted from the seawater. So they're dissolved ions that these plankton extract from the seawater, form their shells, and then once the plankton dies, these shells are much denser and heavier than seawater, so they then sink through the ocean and collect on the seafloor. So some examples of these are the diatoms, and diatoms produce pure silica or opal skeletons, and they can be very significant. There are very significant deposits, diatom opal deposits on the seafloor. Similarly, coccolithophorids, or coccoliths as they're known. So these are quite tiny. This is only 2 microns across, or 2 millionths of a millimetre, but don't be fooled by the small size. This is actually a satellite photograph of a coccolith bloom off the east coast of New Zealand, and this bloom would be several hundred kilometres in length and breadth, and there would be simply uncountable numbers of coccoliths making up this bloom. So this is all calcium carbonate being precipitated, extracted from seawater, dissolved calcium and dissolved carbonate ions being extracted from the seawater by those tiny plankton, formed into these shells, which then you can see here, and then once the coccoliths die, these shells then sink to the bottom of the seawater. A similar zooplankton this time, rather than a phytoplankton, is the foraminifera, and they similarly produce calcium carbonate shells. The scales missing here, this is about 1 millimetre across. In total, this might be 4 or 5 millimetres, and they form these little shells of calcium carbonate that also accumulate in very significant quantities on the seafloor. We have a similar range of not plankton, but rather benthic organisms that also precipitate their skeletons and shells directly from seawater. So we have mollusks, like these ones here, the Anodara that you find down in the estuaries and lagoons on the south coast of New South Wales. There's a giant clam here. They form their shells out of calcium carbonate. That's it. Both the calcium and the carbonate ions are extracted from seawater. And again, they form very, very large amounts of this calcium and carbonate is extracted from seawater to the extent where you can produce huge structures like the Great Barrier Reef that are several 1,000 kilometres long and can be seen from space, as in this diagram here. Another example, a bit like the diatoms, are sponges. So there's a particular group of sponges that produce glass sponges that are made out of pure opaline silica, very much like the diatom produce their frustrals from opaline silica. I mentioned before that whenever we have so when we have organisms producing organic matter in the surface ocean or shells like the plankton, when these organisms die, that organic matter and also the shells tends to sink through the ocean and collect and can collect on the seafloor. So here we just have a picture of a wide variety of different plankton. So these are living plankton. And then we also have things like fecal pellets from fish and zooplankton that are excreted, and those fecal pellets descend or sink very rapidly to the floor of the ocean as well. These are known as well as fish poo or zooplankton poo, and in each case these transport elements and ions to the seafloor as well. Sea spray is another logical transfer of dissolved salts out of the ocean